All right, in today's lecture, we're going to cover the section 4.4 material on the logistic equation. So in this first example, we'll present the logistic equation, look at its solution, and see that it has some more realistic properties as opposed to the exponential growth model. So let's introduce some notation. Here, y of t is going to denote the population size at some non-negative time t, and we will assume that the derivative of y with respect to t, that is the rate at which our population size changes, is given by the following differential equation. We've got ry times 1 minus y over k, where r and k are positive constants. And we have some initial condition, y of 0 is equal to y naught, which is some non-negative value representing our initial population size. So this differential equation, which is representing population growth, is what is called the logistic growth equation, and it's a little more realistic than the exponential growth model. So in part A of this example, we're asked to solve this logistic growth equation, and it is a separable equation. So in order to solve this equation, we would start by separating our variables. So if I move everything with a y to the left-hand side, we would have dy over y times 1 minus y over k is equal to, if I move everything with a t to the right-hand side, I have the constant r times dt. So now, once we've separated our variables, we can integrate on both sides. And to integrate the function on this left-hand side, well, we see it's a fraction. So we could try a substitution. Here, a substitution doesn't work out very well, and we're going to have to make use of partial fractions to integrate this. So before we look at the partial fraction decomposition, let me rewrite this function in terms of y in a little bit simpler form. So if I were to multiply the numerator and denominator of this fraction by k, I would have k over y times k minus y dy, and this is equal to the integral of r dt. So let's look at the partial fraction decomposition for this function on the left. So here we're going to let k over y times k minus y be decomposed in the form a over y plus b over k minus y. Since our denominator was the product of two distinct linear factors, our decomposition would take this form. And to solve for a and b, we could multiply through by our common denominator, which would give us k is equal to a times k minus y plus b times y. So if I want to solve for a, I could substitute y equals 0 into this equation to eliminate the b term, and we're left with k is equal to a times k, which implies that a is 1. And to solve for b, if we let y equal to k, we have k is equal to b times k, so b is also 1. So looking at this integral that we had on our left-hand side in terms of its partial fraction decomposition, we have 1 over y plus 1 over k minus y dy, and the right-hand side is still the integral of r dt. So on this left-hand side, when we integrate, we have the natural log of absolute value y minus the natural log of absolute value k minus y is equal to RT plus C. Again, for these separable equations, we can always group all of our constants of integration on one side. Now from here, we'd like to try to solve for y explicitly. So the way that I can go about doing this would be first to combine the two natural logarithm terms that I have on my left-hand side. Now recall that the difference of two logarithms with the same base is the same as log of the ratio of these quantities, y over k minus y. This is equal to RT plus C. So now to eliminate the logarithm, we can exponentiate on both sides, and we have y over k minus y is equal to c e to the RT. Now again, that constant c out in front is coming from the fact that e to the c can just be considered as a new arbitrary constant c. So now to solve for y, we can multiply through by our denominator, k minus y, and then distribute the c e to the RT, and we have c k e to the RT minus c e to the RT times y. So grouping all of our y terms on the left-hand side, we have y plus c e to the RT times y is equal to ck e to the RT. So on this left-hand side of our equation, we can factor out a y. We're left with 1 plus c e to the RT is equal to ck e to the RT. And so solving for y, we have y as a function of t is ck e to the RT divided by 1 plus c e to the RT. So this is the general solution of that logistic growth equation, but we need to solve for the constant c, making use of our initial condition. Now, the initial condition that we were given was y of 0 is equal to y naught. Now, we could make use of that initial condition to solve for our constant c a little bit earlier in our problem. So here, when we look at this line of our work above, we have c e to the RT is equal to y divided by k minus y. So if we apply our initial condition, at this stage of the problem, we have y naught over k minus y naught is equal to c times e to the 0. Now e to the 0 is just 1, so we have our constant c as y naught over k minus y naught. So let's take that constant c and substitute it into our general solution that we found below. So that would leave us with y of t is equal to y naught times k over k minus y naught all times e to the RT power all over 1 plus c, which was y naught divided by k minus y naught times e to the RT power. So we can simplify this solution a little bit if we were to multiply our numerator and denominator by this common factor k minus y naught that appears in the numerator and denominator, and we're left with y of t is equal to y naught times k e to the RT all over k minus y naught plus y naught e to the RT. or what you would typically see for the solution in a mathematics textbook is what we would get if we simplify this equation a little bit further. So in order to simplify this, we could multiply our numerator and denominator through by e to the negative RT. And what we're left with is y of t is equal to y naught times k all over k minus y naught times e to the negative RT plus y naught. So this is the solution of the exponential growth model in terms of the initial population size, this constant k, and r. So we see in this first part of our example that it is pretty tedious to solve this logistic growth equation explicitly. But for any problem that we're asked about, if we know the initial population size, this constant k, and our growth rate r, then we now have this equation, and we can substitute those values directly into this equation to find our population size at any given time. We wouldn't want to go through this full solution every time that we're given a new set of values for the initial population or our growth rate. Now, one thing which we haven't discussed about this equation yet is what is the meaning of this constant k. Our constant r out in front is a growth rate. It's similar to the growth rate that we saw for the exponential growth model. But what about this constant k? So in the next part of this example, part B, we are asked to determine the limiting behavior of our population as time approaches infinity, and then determine what is the biological meaning of that constant k. So let's recall what we found for our solution in part A. Y of t was given by y naught times k all over k minus y naught times e to the negative RT plus y naught. So if we let t approach infinity, let's look at what we have for the limiting value of our population size over time. Now, the only term that depends on t in our equation is this e to the negative RT term. And since r is a positive constant, we have e to the negative RT power will decay to 0 as t becomes large. So what we're left with is a numerator of y naught times k divided by y naught. So our y naught terms can be canceled, and we're left with k as the limiting value of our population size y of t. So what is the biological meaning of this constant? Well, it represents the maximum sustainable population size for a given species. It's often called the carrying capacity of the population. So remember, one unrealistic feature of the exponential growth model that we saw in our earlier section was that the population size becomes unbounded. And we know that realistically there's an upper limit to a population size for any species. So in summary here, this constant k is the maximum sustainable population size, or sometimes called the carrying capacity of our population. So any problem which references a carrying capacity is talking about this constant k. So in the last part of this section, we'll talk about one other model for population growth, which is even a little more realistic than that logistic growth model. It's a model which accounts for something called the Ali effect. So let's discuss first what is the Ali effect. So here we'll define it. Any sexually reproducing species may experience a disproportionately low recruitment rate when the population density falls below a certain level due to a lack of suitable mates. And this phenomenon is what's called the Ali effect. So for instance, the way I typically try to explain this to students is by saying, okay, let's assume that the population density in Texas falls below, maybe 100 people in the entire state. So at that point, it gets to be very difficult for individuals to find suitable mates, and we see a disproportionate decrease in the recruitment or birth rate. So let's look at a model which accounts for the Ali effect. So here we will again let y of t denote our population size at a given time. And we will assume that the rate at which our population changes, that is the derivative of y, is given by r times y times 1 minus y over k. So it starts just like the logistic growth model. And then we have this extra factor of y minus a. And an initial condition, y of 0 is y naught, which is, again, our initial population size. And these constants, r, a, and k, are positive constants where the value of a lies between 0 and k. So here we are asked to, in part A, find all of the equilibria for this equation and determine their stability. So we want to know for this population model what's going to happen with our population size in the long run. So to find the equilibria of a differential equation, we're going to let our derivative, dy dt, which is given by r times y minus a times 1 minus y over k, and set it equal to 0. So it follows that there are 3 equilibrium values for y. We could either have y is equal to 0, y is equal to a, or if this third factor, 1 minus y over k, is equal to 0, we find that y would have to be k. So in the first part of this problem, we find there are 3 equilibrium solutions, 0, a, and k, and we're asked to determine their stability. So for stability, we can make use of our graphical approach, where we would plot the derivative of our function as a function of y itself. And here we find that there were 3 equilibrium solutions. Those are our horizontal intercepts at 0, a, and k. And we're interested in where our derivative is positive or negative within these intervals. So let's start by looking at a value between 0 and a. So we don't need to choose a specific value, but let's just keep in mind here that we're going to choose some number that lies between 0 and a, so we're less than a. And let's look at the terms of our differential equation to see whether they're positive or negative. So if y is greater than 0, then our first term, r times y, is positive. If y is less than a, then y minus a is going to be a negative value. And if y is less than a, well, we were told a lies between 0 and k, then if we're taking a number less than a, that means we're also less than the value k. So this third factor, 1 minus y over k, if y is something less than k, we have 1 minus some number less than 1, which would be a positive. So we find the product of a positive, a negative, and a positive is a negative number. So the graph of our derivative falls below the horizontal between 0 and a. And now let's look at the interval from a to k. If we choose a value of y that is greater than a but less than k, let's look at the terms of our differential equation. We have r times y would be positive since y is positive. Y minus a is now positive since y is greater than a. And if y is less than k, this last factor, 1 minus y over k, is still positive. So the product of these three positive terms would give us a derivative which is positive on that interval. And if we look at values of y that are greater than k, we would have our first term, r times y, as being positive, y minus a as being positive, and our last term, 1 minus y over k, if k is greater than, or if y is greater than k, then that last term now becomes negative. Now, in this example, we wouldn't need to consider values of y to the left of 0, since y is a population size, and we can't have a negative value for our population size. So based off this phase diagram that we're looking at, we find that between 0 and a, the values of y are decreasing. Between a and k, the values of y are increasing. And for values of y that are greater than k, y is decreasing. So we find the following stability results. The 0 equilibrium is stable. The equilibrium A is unstable. And the equilibrium K is stable. So what we find here is that there's two stable equilibrium solutions, either 0 or K. One of these represents population extinction, the 0 equilibrium, and the other value, y equals k, would represent survival of the population approaching the carrying capacity k. So in part B of this example, we're asked, what is the biological meaning of this constant A? So we can see from our phase line diagram that A is sort of a critical threshold population. If our population ever falls below that value of A, then our solutions are approaching 0. And if the population size is above A, then our solutions will approach this carrying capacity. So the biological meaning of that constant A is a threshold population below which we see extinction of that population. So here, y equals A is a critical population size below which extinction occurs. So we see in this section a couple of different models, the logistic growth model and this model including an Ali effect, which are both more realistic than